So thus far we discussed small signal models and mismatch, etc. So the one thing that is left out is noise. So how we get random noise in electronic circuits. How many of you are familiar with noise models of devices for resistors and MOSFETs and so on? The term noise sometimes is used for everything other than signal. That's not what we mean here. Noise here means random noise that's generated in electronic components like resistors, MOSFETs, etc. So sometimes even interference, that is unwanted signals that come into your signal path is termed noise. But here we are not talking about that. We are talking about some random phenomena that go on inside the device itself to create the noise. Okay. What do we mean by this? Let's say we have a resistor R connected to a voltage source V. What is the current? It should be V by R. This is what is familiar to us. Physically, a resistor could be a bar of some resistive material, it doesn't matter what. Let's say V is a DC quantity, that is, it's not changing with time. And if you plot this current I of t versus time, everything that we know so far says that the current will be a constant V by R. Okay, that's not changing with signal. But if we did measure the current I of t, you measure the current I through any cross section of the resistor. It turns out that the average value is V by R, but instantaneous values can be both above and below this value. Okay, so the waveform may look something like this. This is my depiction of some random signal whose average value is V by R. Okay, so the actual current will be V by R plus some noise current that varies with time. Okay. Why does this happen? Random motion of electrons. Even if you don't have any voltage applied, the electrons in let's say a bar of resistive material are not going to stay still, right? They will be moving back and forth randomly, and how much they move depend on the temperature of the resistor. Okay. So if you were able to take a cross section of the resistor and look at the electrons, there will be some moving this way and some others moving that way and so on. So on average the flow will be in this direction, and the amount of charge transferred in 1 second will be V by R. Okay. But it's not as though across every cross section you will have a uniform current moving in one direction. Okay. The random thermal motion of electrons creates noise. So this IN is something to contend with, because we want a certain current V by R, and in addition to that we have some random signal. So we need to be able to decide whether this is large or small, and if we make some circuits using this resistor, whether this will bother you or not. Okay. So far it's clear. Noise is the result of random motion of electrons in the resistor, and on average the current will be V by R if you apply voltage V across the resistor R, but the instantaneous value will be above and below this. Okay. Now some properties of this noise through the resistor. First of all, its average value is 0. So the average value of the current I of t is V by R, as you expect. Okay. And if you look at the instantaneous values, it turns out that you look at any two time instants, the noise values are uncorrelated. So you can't say anything about IN at T2 given IN at T1. Okay, they are independent random variables. Of course, it's implied here that T2 is not equal to T1. Okay. And it also turns out that if you take a number of resistors, apply the same voltage V across all of them, and measure the noise voltage at the same instant through all the resistors, they will also be uncorrelated from each other. Okay. The noise in one resistor has nothing to do with noise in other resistors. They are uncorrelated. So the noise currents are uncorrelated from one time instant to another and also from one device to another. But how much is the noise? How will we characterize it? We use the variance of noise and we use the spectral density of noise. Let's say you could somehow sample this value of I of t on an oscilloscope and plot the distribution of the samples. They will be distributed as a Gaussian distribution. Okay. It turns out to be the case. It's a Gaussian distribution with zero mean. What its RMS value is, we will see soon. Now, what is the spectral density of any random quantity? It is the Fourier transform of the autocorrelation function, right? So this is one way to think about it. It also turns out to be for a certain class of random processes. Let's say you take various instances of IN of t. Maybe that's from a number of identical resistors. You put the same V and then measure the random noise through all of them. Okay. And you take its Fourier transform, which is IN of f. And then you average the magnitude square of IN over the ensemble. In this case, you have n resistors, you average it over that. That also is the Fourier transform. The two are equal and it can be mathematically proven to be equal. You may have seen this in your communications classes, that the Fourier transform of the autocorrelation function is the same as the average of IN square of f over the ensemble under some conditions. So in our case, it's very easy to visualize this. We just said that it is uncorrelated for all times, all T1, T2, except when T1 equal to T2. Okay. So what will be the autocorrelation function of such a process when it's uncorrelated for all time separations except for the autocorrelation function of this will be an impulse at tau equal to 0. Okay. And what is the Fourier transform of this? It's a constant. It's a constant over all frequency. Okay. So the spectral density of Y is a constant with frequency, and typically in circuit analysis we use single-sided spectral density, that is, we plot only for positive values of f. All the signals we are dealing with are real, so you can always use the double-sided spectral density, but we choose to use single-sided because it is symmetrical about 0. Okay. Now, what is the meaning of the spectral density? Like, what can I tell from this? Okay, this is some value constant S0 over all frequencies. What does it tell me? How do I find out if I connect this, if I sample this and see it on an oscilloscope or something, what value will I see? How will I find out from this? So, what the spectral density says is that if you pass this process through an ideal filter of bandwidth BW, the resulting output will have a mean square value of S0 times BW. Okay. To figure out how much this noise is in terms of the mean square value, we need to figure out what bandwidth we are interested in. So, if we pass this through a filter of bandwidth BW, the output mean square value will be S0 times BW. Okay. This is assumed to be an ideal filter, ideal brick wall filter. Okay. So, essentially what S0 is, it's called the power spectral density. It's essentially measuring the density of the mean square value of quantity over frequency. Okay. You can think of it as power. In this case, the units are not power. We are still talking about only a current, but it's the density of the mean square value of the process. Okay, over frequency. So, what it means is, if the spectral density at a particular frequency is S of f, and if you look in a narrow bandwidth delta f around this frequency f, the mean square value will be S of f times delta f. Okay. So, given the spectral density, you can find out how much the noise is. How much meaning as in some tangible value, like if you stick it to an oscilloscope, what will you see? That way you can find out, but that really depends on the bandwidth itself. The more bandwidth you have, the greater the variance. Okay. In the particular case of the resistor, it turns out that this S is constant with frequency, but that does not have to be the case. We'll see lots of other instances of noise where the value is not constant over frequency. Okay. So, we know a few things now. The noise can be modeled as an additional current source. That's what it is. The current is supposed to be V by R, but in addition to that, we have some IN, and IN happens to have 0 mean, and it has a spectral density that is uniform over frequency. Okay. So, we characterize the noise. We already know that it's a 0 mean, so we characterize the noise using the spectral density. And what the mean square value is depends on the circuit we are dealing with, because the mean square value depends on the bandwidth, and that in turn depends on what circuit we are dealing with and in what context, what application, etc. So, we will not deal with theory of noise and random processes, etc. We will just use this model to calculate the output noise. In our case, the output noise will be measured either in terms of the spectral density of the output noise or in terms of the mean square value of the output noise. In case of mean square value, we have to sum the value of S of f over a certain range of frequencies. Okay. So, if you take a frequency range from F1 to F2, the mean squared value will be integral of S of f from F1 to F2. Okay. Again, in case of the resistor, it's a trivial integration because S is constant, but that's not always the case. So this is the spectral density of the noise current of a resistor. I'll call it SIM. Okay. And it has a certain value, S0, which is constant over frequency. What are the units of S0? See, if we integrate this over a certain frequency range, okay, we get the mean square value in ampere square. Okay. And this is the mean square value of IN. Okay. So you square it and average it, that is what the mean square value is. Okay. The mean square value of IN has a unit of ampere square, and the density of that over frequency has a unit of ampere square per hertz. Okay. So the mean square value of some noise current has units of ampere square, and the spectral density is nothing but the density of the mean square value over frequency. So it has units of ampere square per hertz. So if you can integrate it in the range of interest, the frequency range of interest, and you will get the variance or the mean square value in ampere square. Okay. So what is the mean square value? For a periodic signal, what you would have done is, you integrate the square of the current over one period. Now in case of a random quantity like this, there is no period, so you just take the limit as t10 goes to infinity, and this gives you the mean square value. Okay. So this is what the mean square value is, and if you are given a spectral density, you can find out the mean square value by integrating it. And what is the value of this? It turns out that in case of a resistor, this value of S0 is 4 kT divided by R, where K is Boltzmann's constant and T is the absolute temperature. Okay, and R is the value of the resistor. As you can see, it depends only on the temperature and the value of the resistor. It does not depend on anything else, like what circuit it is in or any circuit conditions. Okay, it does not depend on the operating point or any such thing. If you have a resistance of value R at a temperature T, this is the noise variance. And also it reflects something that may be intuitively appealing, that if the value of T reduces, the temperature reduces, the amount of noise reduces. Okay, this is what you expect. I just said that the noise is because of random thermal motion of electrons, which does reduce if you reduce the temperature. Okay, at absolute zero there will be no noise. So in fact, for extremely noise sensitive circuits, you will have the whole thing in a refrigerator or in a liquid nitrogen tank. So if you see all the circuits that are made for detection of signals from radio astronomy sources and so on, you will have those things in some cooled cylinder of liquid nitrogen, so that the temperature goes down to low values. So brute force, you reduce this and hence reduce the noise. So here we will use something less brute force, right, and try to see how to minimize the noise, or at least we will be able to calculate the noise. Based on that, we can see how to control the amount of noise. The bottom line is, a resistance R, when it has a voltage V across it, has a current V by R plus some noise. Okay. So the model for the resistor, the model for that will be a noiseless resistor of the same value R. So this gives me the part V by R. Okay. If I have V across it, I will only have V by R. So to that I need to add a noise current IN in the model. Okay. And what is IN? I don't know the instantaneous value of IN, and I don't care also. Okay. It is random noise, and it happens to be white, which is the term used for some noise whose spectral density is uniform across all frequencies. So, if the spectral density is constant with f, such a noise is called white noise, and the noise due to a resistor, the thermal noise in a resistor is white, and the spectral density is 4 kT divided by R, and its units are ampere square per hertz. Okay. So basically, wherever, if you are worried about noise, wherever you have a resistor in the circuit, you replace that with this model, which is a noiseless resistor in parallel with a current source. The current source has a given spectral density. So you calculate the transfer function from this noise source to that output voltage. Okay. So you have some circuit, and every resistor has been replaced with a resistance in parallel with a noise current. Okay. And let's say, just for illustration, that the output of interest for you is some V out. Okay. So how do I find out how much noise is there in V out because of this IN? It is like any other source in the circuit. So I just disable all the other sources and I calculate V out by IN. I have used uppercase here because these things could be frequency dependent. Okay. So this gives me, if I had a source IN, I know what effect it will have on V out. Okay, as a function of frequency. So this is the transfer function from the noise source IN to the output voltage V out. Then what do I do? So I don't know what IN is exactly, right? I don't know IN of T or IN of S. What I know is the spectral density of IN. See, if IN was something like a sinusoid, I know essentially what IN of S is, or in time domain I know it. And so I calculate V out of T or V out of S. Now I don't know that. Okay, it's a random quantity. So what do I do to get a measure of the output noise? So again, I am not interested, or I cannot even calculate the instantaneous value of V out. Okay, V out of T or V out as a function of the Laplace variable, I can't calculate. What I am interested in is in the spectral density of V out also. Okay. From the spectral density, I can calculate the variance or the mean square value. It turns out that the spectral density of this output voltage will be the spectral density of the current IN times the magnitude squared of the transfer function. Okay, let me show the dependence on F explicitly. And where is F in this? So S is, calculate the transfer function for real frequencies F. S will be the magnitude squared of this. It's the spectral density times the transfer function magnitude squared. What is any transfer function H of S? It is some function in the complex plane. SA equals sigma plus j omega. Okay. So the y-axis here, the omega axis, corresponds to the frequencies of sinusoids. Okay. If I look at a particular point omega naught, that represents the sinusoid of frequency omega naught. Or if you want it in terms of hertz, it is f naught equals omega naught by 2 pi. Okay. to calculate the transfer function or to calculate the steady state response of a circuit, I need to find the response to a particular sinusoid. And a sinusoid of frequency omega naught corresponds to S equals j omega naught, or a sinusoid of frequency f naught corresponds to S equals j 2 pi f naught. Okay, so that's what I did there. So I want to calculate the response of the circuit to a certain frequency, certain sinusoidal frequency f. So I substitute S by j 2 pi f. If I have a transfer function as a function of S, then when I substitute S equals j 2 pi f, I calculate the value at this particular point. Okay, and what is that? That will give me the magnitude and phase of the modified sinusoid. If I put in a 1 volt sinusoid at f naught, what comes out at the output? How much its magnitude has changed, how much its phase has changed, is obtained by the value of h of s at this particular point. Okay, that's the meaning of the transfer function, right? So there is a theorem that says that the spectral densities are related by the magnitude squared of the transfer function, and that's what I use to put the square here. Okay, the way we go around calculating noises, we have some models for noise for each of the components, and the quantity of interest is not really the noise across one particular resistor or something. You have some output voltage or output current that is of interest to you. So you calculate the transfer from each of the component noise sources to the output. Then you have to sum all of them. So you calculate the spectral density from each source and sum the spectral densities. And you can sum the spectral densities or the mean square values because the noise from each component is uncorrelated. Okay? So you do this, like if you have 100 components, you have to do this for 100 components, that's all. I said that the noise can be modeled by a noiseless resistor in parallel with a random current source, and the spectral density of the random current source is 4 kT by R. Now, anytime I have resistance in parallel with the current source, I can also equivalently represent it by a resistance in series with a voltage source. Right? This is just circuit theorem, Thevenin and Norton equivalents. So if this is IN and this is R, what is the value of the voltage source here? IN times R. Okay. So if IN has a certain spectral density, what is the spectral density of IN times R? R square. Here the transfer function is not frequency dependent, but it is just a multiplication by R. Okay. So this gets multiplied by R square to give you 4 kT times R. So I call this a random voltage Vm. So S IN is 4 kT by R and S Vn is 4 kT times R. Okay. Vn is IN times R. This is just from transforming the parallel current source and a resistor to a series voltage source and resistor. This, from what we discussed just in the previous few minutes, is SIN R square, gives the spectral density multiplied by R square. So SVN is 4 kT times R. Okay. So here is where the question he asked comes in. So if you look at the current expression, it looks like the noise reduces with increasing resistance. And if you look at the expression for the spectral density of the voltage, it looks like the noise is going to increase if you increase the value of the resistance. So which is right? Is there any contradiction here? So that is one answer, that the two are exactly the same circuit, right? We know from our circuit theorems that this is exactly the same as this. If I have this in some circuit and if I replace it with that, whatever else I calculate, I will get exactly the same answer. That part is true because these are just Thevenin and Norton equivalents of each other. Okay. So if you calculate some output voltage of some given circuit using either of the two models, they give you the same answer. So that tells you that the two are the same. But like what else? So that is, yeah, that's one way of answering it. But if you look at the expressions, it seems like if I didn't know anything else, if someone told me that this is the noise of a resistor, I would try to make all my circuits with as large resistances as possible, okay, because I want low noise. Somebody else knows only this particular expression and they try to make a circuit with as low resistances as possible for low noise. Now, only one of us will have the low noise circuit, right? Let's take a silly circuit. I have a resistive divider. The function of this is not dependent on what value I use. It depends only on the ratio. Okay. So, I can use 1 megohms of resistance or I can use ohms. So, if you are familiar only with the current model, maybe you will go with one way, and if you are familiar only with the voltage spectral density, you will go the other way. So, which way should you go and why? Actually, this will become clearer as we go on. So, it really depends on the quantity of interest, whether you are interested in some output voltage or some output current. Okay. So, if I am interested in a voltage, I am interested in the noise in that voltage, and that does indeed increase with increasing values of resistance. Okay. So, if I am talking about voltage noise in some circuit, I would try to make my impedance levels as low as possible. And if you look at the current noise, it will be proportional to the inverse of the impedance level. Okay. So, if I am interested in the current noise, I will make my impedance levels very high. So, there is no contradiction here. It is true that the current noise does decrease with increasing impedance level and the voltage noise increases with increasing resistance level or impedance level. Is this okay? So, there is no contradiction. The two are equivalent, that you can see straight from the circuit analysis models. This is exactly equivalent to this. But also, the two are measuring different quantities. One is measuring current noise, the other is measuring voltage noise. So, and there is no contradiction if one of them increases with the resistance level and the other one decreases with the resistance level. If we want to find out the noise in any circuit, we replace, let's say we have only resistors, or at least we have noise models only for the resistors. So, every resistor is replaced by the model, okay, which depending on convenience, you can either use the parallel model or the series model, and you calculate the transfer function from each of the noise sources to the output. Okay, and you multiply the spectral density of individual resistor with the particular transfer function, the square root of the transfer function magnitude, and add all of them up. Okay. So, if you have n resistances R1 to Rn, you replace R1 to Rn with noiseless resistors. Noiseless resistors only means that it follows the model that we have been using all along, that V equal to IR, that's all, right? And equivalent noise voltage or current sources. Okay, and in this particular case, I will just say I have used voltages, but it can be currents also. Okay. You calculate transfer functions from all these sources to the, let's say the output is also a voltage V out. Then the output spectral density will be given by the spectral density of the first resistor's noise times the transfer function squared from that noise source so on. Okay. So, this is what you do in any other circuit also. I mean, we will be soon discussing noise models of other components like MOSFETs. So, in that case also you replace each of the components by their models including the noise, calculate the transfer function from each noise source to the output, multiply the spectral density by magnitude squared of that particular transfer function, and add all of the contributions. Okay. We can add all of the spectral densities because the noise from each component is uncorrelated noise from all the other components. Okay. Is the procedure clear? So this is the level at which we work with noise. We won't discuss the theory of random processes or anything. We assume that whenever we have some noise source, we know its spectral density. Then we know how to calculate transfer functions because we know circuit analysis. So putting the two together, we can calculate the output spectral density. Okay. So now if this circuit is driving some other circuit, we can do the same thing. We can take this spectral density, multiply it by the following circuit's transfer function and get its output spectral density and so on. Okay. We will continue the discussion of this in the next week, but please calculate the spectral density of noise in this circuit. Okay. So this is a first order low pass filter, we are all familiar with it. So this is V out, you calculate the spectral density of V out, okay, and you also calculate the RMS value of V out because of noise. Obviously, when you calculate the effect of noise, you disable the input source. Basically, even with Vin equal to 0, it gives you some output. That is the effect of noise. If it was a noiseless circuit with 0 input, it would give you 0 output. And you calculate the integrated output noise over the entire range of frequencies. Okay.